Hello, in this lecture we find out the area of the circle. In the drawing we have quadrilateral ABCD. Inside this quadrilateral we have this circle. We also know that side AB of the quadrilateral is equal to 2 units in its length. Side BC equals to 8 units. Side DC also equals to 8 units. This angle BCD equals to 90 degrees in its length. This angle ABC, it is also equals to 90 degrees. Our mission is to find out the area of this circle. So first of all, we'll do a construction. We will extend side DA and side CB of the quadrilateral until they touch each other. Okay, so here. Actually, this is the touching point of the extended side DA and side CB. We define the touching point, this point, as M. BC is one side of the quadrilateral ABCD, therefore it is absolutely a straight line. When we extended the straight line BC by a straight line, the result is CM. So CM must be also a straight line, because when you extend the straight line by a straight line, the result must be a straight line. So CM is a straight line. If you focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle, this missing angle ABM. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that I mentioned. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of CM at point B to 180 degrees, the missing angle here must be equal to 90 degrees. So in triangle AMB, the right angle ABM, we define angle AMB is theta. Angle AMB equals to theta. This angle equals to 90 degrees. This is the missing angle. The missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta, it is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we'll focus on the right big triangle MDC. On the right triangle MDC, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle here must be also equal to 90 degrees minus theta. In the next step, we will prove that the big triangle MDC is similar to the small triangle MAB. They are both right triangles. So I write it down. The big triangle MDC, the right big triangle MDC, is similar to the small right triangle MBA. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle DCM in the big right triangle is equal to this angle that is actually angle ABM in the small right triangle. Repeat again. Angle DCM equals to angle ABM. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles. So you can say that angle theta equals to itself. You can call to angle theta two different names. Angle theta can be defined as angle DMC. When we relate to angle theta, as it belongs to the big triangle. So the angle DMC, that is angle theta, it is equal to angle theta itself. We can relate to angle theta as angle AMB when we relate to it as it belongs to the small triangle. Repeat again. Here we call to angle theta two different names. This equation means that angle theta equals to itself as a common angle that belongs to both triangles. And finally, we have those two angles that are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle CDM in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees minus theta. Yeah. Again, angle CDM in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually found out that all the three angles in the big triangle MDC are correspondingly similar to all the three angles in the small triangle ABM. Therefore, we actually proved that the big triangle MDC is similar. This is the sign of similar to the small triangle BAM according to angle similarity rule. And for the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. MC in the big triangle over MB in the small triangle is equal to DC in the big triangle over AB in the small triangle. Repeat again. MC over MB equals to DC over AB. What is the length of side MC? From the drawing it is very easy to see that MC equals to MB plus BC. That is to say MC equals to MB plus BC, that is 8. So in total MC equals to MB plus 8. mb plus 8 over mb equals to DC is 8 and AB is 2. 8 over 2 is 4, so MB plus 8 over MB equals to 4. We multiply this equation by MB and we get that MB plus 8 equals to 4 MB. Here we subtract MB from this equation and finally we get that 8 equals to 4 MB minus MB is 3 MB. We divide this equation by 3 and finally we will get that MB equals to 8 over 3 units. MB equals to 8 over 3 units. Line segment MB equals to 8 over 3 units. In the next step, we will implement the Pythagoras theorem on the right small triangle MAB. Okay. Here by PT is a variation from Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle AMB is AM, so the square of the hypotenuse is AM squared, and it must be equal to AB squared plus MB squared. Repeat again, according to the Pythagoras theorem, in the right triangle AMB, AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB is 2, so AB squared is 2 squared, that is 4, plus MB squared. MB is 8 over 3, so MB squared is 8 over 3 squared. So AM squared equals to 4 plus 8 over 3 squared equals to 8 squared, that is 64, over 3 squared, that is 9. Here we'll multiply 4 by 9 and then we'll divide it by 9 in order to have a common factor with 64 over 9. And we get that AM squared is equal to 4 times 9, it is 36, so in the numerator we will have 36 plus 64 over 9. 36 plus 64, it is 100 over 9. Here we take a root out of this equation, and finally we will get that the length of the hypotenuse AM is equal to the square root of 100 over 9. The square root of 100 is 10, and the square root of 9 is 3. So in total, AM equals to 10 over 3 units. The hypotenuse AM it is equal to 10 over 3 units. So we write examine the original point that AM equals to 10 over 3 units. In the next step, I will present to you rule number 1, and we will implement the rule in our drawing. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. AB is tangent to this circle at point M. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule number 1. We can implement rule number 1 in our drawing. First of all, we define the center of this circle. This point is O. AB is tangent to the circle at this point. We define the point of tendency as M. And then we join points O and M together by a straight line. Point O is the center of the circle. Point M is the point on the circle itself. Therefore, OM is the radius of the circle that we will define as X. We have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle is also equal to 90 degrees according to rule number 1. BC is tangent to the circle at this point. We will define the point of tendency as N. Then we will join points O and N together by a straight line. ON is the radius of the circle that is equal to X. The radius ON is drawn to point N, that is the point of tendency of tangent BC with this circle. Therefore, tangent BC will be perpendicular to the radius NO. If BC is perpendicular to NO, it means that this angle equals to 90 degrees. And this angle will be also equal to 90 degrees according to rule number 1. So in quadrilateral MOBN, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3, 270 degrees, plus the missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So in order to complete the sum of the angles in this quadrilateral to 360 degrees, the missing angle must be equal to 90 degrees. The next step, we will do a construction. We will draw perpendicular on BC in such a way that it will be also tangent to the circle. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the point of tendency of tangent with BC as point Z. This is actually the point here. We go perpendicular, so it is the point at this point we have angle of 90 degrees, so this is actually equal to 90 degrees and this is equal to 90 degrees. That is the touching point between the perpendicular and side BC. So this point is the point of tendency of the perpendicular with this circle. We define the point of tendency as point T. Then we will extend the tangent ZT until it touches side DM. We define the touching point of the extended ZT with side DM as L. We join points O and T together by a straight line. OT is the radius of the circle that is equal to X. The radius OT is drawn to point T, that is the point of tendency of tangent LZ with this circle. And therefore LZ will be perpendicular to the radius OT. Tangent LZ will be perpendicular to the radius OT. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. In quadrilateral ONZT we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Angle MOT, this angle is equal to 90 degrees plus 90 degrees, it is 180 degrees. Any angle that is equal to 180 degrees must be a straight line. If MOT is a straight line, then MT is also a straight line. But MT touches the circle at points M and T, therefore MT is a chord. Line segment MT is a chord that passes through point O, that is the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. Therefore, MT is the diameter of the circle. You can write down here that line segment MT is the diameter of the circle. We focus on quadrilateral MTBZ. In quadrilateral MTBZ, we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral MTBZ as a rectangle. We know that the opposite sides of rectangle MTBZ must be equal to each other. That is to say, side MT equals to side BZ. In rectangle MTBZ, side MT equals to side BZ. And from this equation, we derive that BZ is also the diameter of the circle. BZ is the diameter of the circle. Line segment BZ is the diameter of the circle. The diameter of any circle is twice as long as the radius, and the radius of this circle is x, therefore the diameter BZ must be equal to 2x. BZ equals to 2x. You can write here that the length of line segment BZ is 2x. We'll focus on the right triangle LZM. In the right triangle LZM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. In the next step, we will prove that the right big triangle MLZ is similar to the small right triangle MAB. Why those two right triangles are similar to each other? So I write it down, the right triangle, the right big triangle MLZ is similar to the right small triangle AMB. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle LZM in the big triangle is equal to angle ABM in the small triangle. So I'll repeat again. angle LZM in the big triangle is equal to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles, so we can say that angle theta equals to itself. You can call to angle theta two different terms. Angle theta is angle LMZ, and it is equal to itself. Angle theta can be defined also as angle AMB. Repeat again. Here we define angle theta with two different terms. This equation means that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle MLZ in the big triangle, and it is equal to angle MAB in the small triangle. Repeat again. Angle MLZ in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big triangle MLZ are correspondingly equal to all the three angles in the small triangle AMB. Therefore, we actually proved that the big triangle MLZ is similar to the small triangle AMB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that MZ in the big triangle over MB in the small triangle is equal to LZ in the big triangle over AB in the small triangle. I'll repeat again. MZ over MB equals to LZ over AB. What is the length of MZ? From the drawing it is very easy to see that MZ equals to MB plus BZ. That is to say, MZ equals to MB, that is 8 over 3, plus BZ, that is 2x. So in total, MZ equals to 8 over 3 plus 2x. Over MZ, that is 8 over 3. It is equal to LZ. LZ is unknown, so we leave it as it is. Over AB. AB is 2, so we will substitute AB by 2. Okay. Here, we'll multiply 2x by 3 and then we'll divide it by 3 in order to have a common factor with 8 over 3. And we'll get that 8 plus 2x times 3 is 6x over 3 over 8 over 3 is equal to LZ over 2. Here we have 3 in the numerator, 3 in the denominator, so 3 will get cancelled. And finally we found out that 8 plus 6x over 8 is equal to LZ over 2. Repeat again. I actually found out that 8 plus 6x over 8 equals to LZ over 2. Here we'll cross multiply this equation and we'll get that 2 times 8 plus 6x equals to 8 LZ. Here we'll divide this equation by 2 and finally we get that 8 plus 6x equals to 8 over 2 is 4, so it is 4 LZ. Here we will divide this equation by 4 and finally we will get that LZ is equal to 8 over 4 is 2 and 6x over 4 is 1.5x. So in total we found out that the length of line segment LZ is 2 plus 1.5x. So you can write down in the original drawing that this line segment LZ it is equal to 2 plus 1.5x in its length. Because of the fact that the big right triangle LZM is similar to the small right triangle ABM, addition relationship exists between their sides. The following relationship exists between their sides. MZ in the big triangle over MB in the small triangle is equal to LM in the big triangle over AM in the small triangle. Repeat again. MZ over MB equals to LM over AM. Here, I've already explained to you that MZ equals to 8 over 3 plus 2x. MB is 8 over 3 and it is equal to LM. What is the length of the hypotenuse LM? From the drawing it is very easy to see that LM equals to LA plus AM. That is to say LM equals to LA plus AM, that is 10 over 3. So in total LM equals to LA plus 10 over 3. And AM is 10 over 3. So here we'll multiply 2x by 3 and then we'll divide it by 3 in order to have a common factor with 8 over 3. So we have here 8 plus 2x times 3 is 6x over 3 over 8 over 3. That is equal to, here also we'll multiply LA by 3 and then we'll divide it by 3 in order to have a common factor with 10 over 3. 3 times LA is 3LA plus 10 over 3 over 10 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled Here also in this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 will also get cancelled. So what is left from this equation after we cancel 3 on both sides of the equation? We have in this side of the equation we left only with 8 plus 6x over 8, that is equal to 3LA plus 10 over 10. So here we'll cross multiply this equation. And we'll get that ten times 8 plus 6x is equal to 8 times 3LA plus 10. We'll open the brackets on both sides of the equation. 10 times 8 is 80, plus 10 times 6x is 60x. That is equal to 8 times 3LA is 24LA. 8 times 10 is 80. So here we have 80 on both sides of the equation, so 80 will get cancelled, and we're left only with 60x. That is equal to 24 LA. So here we'll divide this equation by 24, and finally we'll get that the length of line segment LA, it is actually equals to 60x over 24. 60x over 24 is 2.5x. So you can write down in the original drawing the length of this line segment LA or AL is equal to 2.5x. In the next step, I will copy quadrilateral ALBZ in a new page. So actually this is quadrilateral ALBZ that I copied from the original drawing. This quadrilateral ALBZ blocks a circle. This is the circle that the quadrilateral blocks, so I copied the circle in the new drawing. The circle and the quadrilateral touch each other at 4 points. Actually, they have 4 points of tendencies. 1, 2, 3, 4. We define the first point as M. We define the second point of tendency as N. We define the third point of tendency ST. And finally, we define the fourth point of tangency of the circle with this quadrilateral as G. In the next step, I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Point P is the common external point. From the point P, we have two tangents to the circle, tangent PA and tangent PP. And according to rule number 2, whenever you draw from a common external point to tangent to the circle, they must be equal to each other. In this case, PA equals to PP. We can implement rule number 2 in our drawing. We focus on the common external point, point A. From the common external point, point A, we have two tangents to the circle. The first tangent is AM, the second tangent is AN. And according to rule number 2, they are equal to each other. That is to say, AM equals to AN, AM equals to AN, AM equals to AN. So actually, if AM is A, then AN, if AM is A, then AN must be also equal to A. In the next step, we focus on the common external point, point B. From the common external point, point B, we have two tangents to the circle, tangent BN and tangent BT. And according to rule number 2, they are equal to each other. That is to say, BN equals to BT. So if BN is B, then BT must be also equal to B. The next step, we'll focus on the common external point, point Z. From the common external point, point Z, we have two tangents to the circle, tangent ZT and tangent ZG. According to rule number 2, they are equal to each other. So ZT is equal to ZG. So if ZT is C, then ZG also must be equal to C. And finally, we focus on the common external point, point L. From the common external point, point L, we have two tangents to this circle, tangent LM and tangent LG. And according to rule number 2, they are equal to each other. That is to say, LM equals to LG. So actually, if LM is D, then LG must be also equal to D. So, in the next step, we will add side AL to side BZ. We'll add side AL to side BZ. And this quadrilateral AL BZ. So AL plus BZ. What is the value of AL plus BZ? It's very easy to see from the drawing that the length of AL is A plus D. So we substitute AL by B plus D, by A plus D. AL is A plus D. AL is A plus D. So we substitute AL here. We substitute AL by A plus D plus BZ. From the drawings, it's very easy to see that BZ equals to B plus C in its length. So we substitute BZ here by B plus C. In total, we found out that AL plus BZ equals to A plus D plus B plus C. We can change the order of the variables. Actually, the value of the expression A plus D plus B plus C is equal to A plus B plus C plus D. We just change the order of the variables. In the next step, we will add side AB to side LZ. AB plus LZ. AB plus LZ. From the drawing, it is very easy to see that LB equals to A plus B, so we substitute AB by A plus B plus LZ. Here LZ, from the drawing, it is very easy to see that LZ equals to C plus D. We substitute LZ here by C plus D. Okay. So actually, I found out that AL plus BZ equals to A plus B plus C plus D, but AB plus LZ also equals to A plus B plus C plus D. Therefore, those two expressions must be equal to each other. Okay. I know that AL plus BZ, it is equal to AB plus LZ. Okay, they are both equal to the same expression, therefore they are equal to each other. So AL plus BZ equals to AB plus LZ. The value of AL is 2.5x, therefore we'll substitute AL by 2.5x. The value of BZ here, it is 2x, so we substitute BZ by 2x. And it is equal to AB. AB is 2 according to what is given us the equation, therefore we substitute AB by 2 plus LZ. We already found out that LZ equals to 2 plus 1.5x. So we substitute LZ in the equation by 2 plus 1.5x. In conclusion, we found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x. And it is equal to 2 plus 2 is 4 plus 1.5x. So here we'll substitute we'll subtract 1.5x from this equation, and we'll get that 4.5x minus 1.5x is 3x. That is equal to 4. Here we'll divide this equation by 3. And finally we get that x equals to 4 over 3 units. That is to say, the radius of this circle x, it is equal to 4 over 3 units. And we also know that the area of any circle here the squared brackets is the sign for the area, so the area of any circle equals to pi times the radius square. If the r is the radius, it is pi r squared. In our specific circle, we define the radius as x, therefore the area will be pi x squared. We just right now found out that x equals to 4 over 3 units, therefore we substitute x in this equation by 4 over 3, and we will get that it is equal, the area equals to pi times x squared. X is 4 over 3. Therefore, x squared is 4 over 3 squared. So in conclusion, found out that the area of our circle is equal to pi times 4 over 3 squared. That is to say, it is equal to pi times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, found out that the area of this circle, it is equal to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. And that is the answer to our question. In the next step, I will summarize the lecture. So in the drawing, we have quadrilateral ABCD. Inside this quadrilateral, we have this circle. We know that side AB equals to 2 units, side BC equals to 8 units, side DC also equals to 8 units. This angle DCB equals to 90 degrees. This is angle ABC that is also equals to 90 degrees in its size. Our mission is to find out the area of this circle. So in order to find out the area of this circle, we did a construction. That is to say, we extended side DA and side BC of the quadrilateral by a straight line until they touch each other in this point. This is the touching point of the two extended sides. We define the touching point as M. Side BC is one side of the quadrilateral, therefore it is absolutely a straight line. When we extended the straight line BC by a straight line, the result CM must be a straight line, because when you extend a straight line by a straight line, the result must be a straight line. So CM is also a straight line. So if we focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle here must be equal to 90 degrees in order to complete the sum of the angles at the upper side of CM at point B to 180 degrees. The missing angle here must be equal to 90 degrees. So in the right triangle ABM, we define this angle AMP as theta. So this angle equals to theta according to our definition. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Then we focus on the big right triangle MDC. On this big right triangle MDC, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus theta. Then we prove that the big triangle MDC is similar to the big small right triangle ABM. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is the common angle, it belongs to both triangles. Therefore, we can say that angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually prove that all the three angles in the big right triangle DCM are correspondingly equal to all the three angles on the small right triangle ABM. Therefore, we actually proved that the big right triangle MDC is similar to the small right triangle ABM according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule. exactly as we proved in our two triangles. Okay, from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that MC in the big triangle over MB in the small triangle is equal to DC in the big triangle over AB in the small triangle. I repeat again. MC over MB equals to DC over AB. What is the length of MC? From the drawing it is very easy to see that MC equals to MB plus BC, that is to say MC equals to MB plus BC, that is 8. In total, MC equals to MB plus 8. So MC equals to MB plus 8 over MB, it is equal to DC is 8, AB is 2. 8 over 2 is 4. So MB plus 8 over MB equals to 4. We multiplied this equation by MB and found out that MB plus 8 equals to 4MB. We subtracted MB from this equation and found out that 8 equals to 4MB minus MB is 3MB. So 8 equals to 3MB. We divided this equation by 3 and finally found out that MB equals to 8 over 3 units. This line segment MB equals to 8 over 3 units. Then we implemented the Pythagoras theorem on the right triangle MAB. According to the Pythagoras theorem on the right triangle AB, AM squared equals to AB squared plus BM squared. It again, the right triangle AB, AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB is 2, so AB squared is 2 squared, that is 4, plus MB squared. MB is 8 over 3, so MB squared is 8 over 3 squared. Okay, so AM squared equals to 4 plus 8 over 3 squared. 8 over 3 squared equals to 8 squared, that is 64, over 3 squared, that is 9. Here we multiplied 4 by 9 and then we divided by 9 in order to have a common factor with 64 over 9. So AM squared equals to 4 times 9 is 36 plus 64 over 9. 36 plus 64, it is 100 over 9. We took a root out of this equation and finally found out that AM equals to the square root of 100 over 9. The square root of 100 is 10 and the square root of 9 is 3. So in total, in conclusion, found out that the hypotenuse AM equals to 8 over 3 units in its length. Here the hypotenuse AM equals to 8 over 3 units. Then I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, tangent to a circle is perpendicular to the radius drawn to its point of tendency. Tangent AB is tangent to this circle at point M. The radius OM is drawn to the point of tendency, that is to say it is drawn to point M. That is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to this rule, rule number 1. So I actually implemented rule number 1 in our drawing. First of all, we define the center of this circle, this point as O. AB is tangent to this circle at this point, point M. We join points M and O together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that we defined as X. We have the radius OM that is drawn to point M, that is the point of tendency. Whenever you have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees. This is according to rule number 1. BZ or BC is tangent to the circle at point N. We join points O and N together by a straight line. ON is the radius that is equal to X. The radius ON is drawn to point N, that is the point of tendency, of tangent BZ with the circle. Whenever radius that is drawn to the point of tendency, then the tangent BZ will be perpendicular to the radius NO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Then in quadrilateral OMBN, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Plus the missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, the missing angle here must be equal to 90 degrees. Then we draw perpendicular on BC in such a way that it will be also tangent to the circle at point T. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We extended the perpendicular ZT until it touches side DM at point L. T is the point of tendency of tangent LZ with the circle. We joined points O and T together by straight line. OT is the radius that is equal to x. The radius OT is 1 to point T, that is the point of tendency. Whenever you have a radius that is 1 to the point of tendency, then tangent LZ will be perpendicular to the radius TO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So in quadrilateral OTZN, we have 1, 2, 3 right angles. Therefore the fourth angle must be equal to 90 degrees. According to the rule that I mentioned. So angle TOM, this angle TOM equals to 90 degrees plus 90 degrees, it is 180 degrees. Any angle that is equal to 180 degrees must be a straight line. Therefore TOM is a straight line. TOM is a straight line, but TOM also touches the circle points T and M. Therefore TOM is a chord that passes through point O, that is the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. Therefore Tm is the diameter of the circle. So you can write here that Tm is the diameter of the circle. We focus on quadrilateral MTBZ. In quadrilateral MTBZ we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral MTBZ as a rectangle. And we know that the opposite sides in any rectangle, and especially in rectangle MTBZ, are equal to each other. That is to say, MT equals to BZ. So you can write here that MT equals to BZ, and from this equation, MT equals BZ equals to MT equals to the diameter. We will derive that BZ is also the diameter of the circle. But the diameter of any circle is twice as long as the radius. And the radius is x, therefore the diameter must be 2x. The diameter of BZ must be equal to 2x in its length. Here, the diameter BZ must be equal to 2x in its length. So we focused on the right big triangle LZM. In the right big triangle LZM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle must be equal to 90 degrees minus theta. Then we proved that the big right triangle LZM is similar to the small right triangle ABM. Why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles. So we can say that angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that the right triangle LZM, the right big triangle LZM, is similar to the small right triangle ABM according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that MZ in the big triangle over VM in the small triangle is equal to LZ in the big triangle over AB in the small triangle. I'll repeat again. MZ over MB equals to LZ over AB. mz is 8 over 3 plus 2x, mb is 8 over 3. What is the length of Lm? Lm is La plus Am. That is to say, Lm is La plus Am, that is 10 over 3. So in total, Lm is La plus 10 over 3. Okay. So here, mz is 8 over 3 plus 2x, mb is 8 over 3, ab is 2, and this is actually here. Actually, we found out that Zm over Bm is equal to Lz over AB. Again, Zm over Bm equals to Lz over AB. Okay, here Zm is 8 over 3 plus 2x, Mb is 8 over 3, Lz is unknown, and AB is 2. Here we multiplied 2x by 3 and then we divided by 3 in order to have a common factor with 8 over 3. So here in the numerator we have 8 plus 2x times 3 is 6x over 3 over 8 over 3 equals to Lz over 2. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And we left only with 8 plus 6x over 8 over, that is equal to Lz over 2. Repeat again. We left with 8 plus 6x over 8, that is equal to Lz over 2. Okay. Lz over 2. Here we first multiplied this equation and we found out that 8 times Lz equals to 2 times 8 plus 6x. We divided this equation by 2 and we found out that 8 plus 6x equals to 8 over 2 is 4. So 8 plus 6x equals to 4 Lz. We divided this equation by 4 and finally found out that the length of line segment Lz is equal to 8 over 4 is 2 plus 6x over 4 is 1.5x. So in total, Lz equals to 2 plus 1.5x. Here, line segment Lz equals to 2 plus 1.5x. Because of the fact that the big triangle LZM is similar to the small triangle ABM, we will derive that the following and that additional relationship exists between their sides. We derive that Zm in the big triangle over Bm in the small triangle equals to Lm in the big triangle over Am in the small triangle. Repeat again, Zm over Mb equals to Lm over Ma. We have already found out that Zm equals to 8 over 3 plus 2x and Mb equals to 8 over 3. What is the length of Lm? Lm equals to La plus Am. That is to say, Lm equals to La plus Am, that is 10 over 3. So in total, Lm equals to La plus 10 over 3. Here we substitute Lm by La plus 10 over 3 and Ma, here Am equals to 10 over 3. So here we multiplied 2x by 3 and then we divided by 3 in order to have a common factor of 10 over 3. And here also we multiplied La by 3 and then we divided it by 3 in order to have a common factor of 10 over 3. So in the numerator we have 8 plus 2x times 3 is 6x over 3 over 8 over 3. That is equal to 3 times La is 3La plus 10 over 3 over 10 over 3. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. Here also we have 3 in the numerator and 3 in the denominator, so 3 also here will get cancelled, and we left only with 8 plus 6x over 8 equals to 3LA plus 10 over 10. Here we cross multiply this equation and we found out that 10 times 8 plus 6x equals to 8 times 3LA plus 10. We opened the brackets on both sides of the equation and we found out that 8 times 10 is 80 plus 8 times 6x is 60x. It is equal to 3 times LA is 24LA plus 8 times 8 is 80. So we have 80 on both sides of the equation, so 80 will get cancelled. And we left only with 60x, that is equal to 24LA. We divided this equation by 24 and finally found out that the length of line segment LA equals to 60x over 24, it is equal to 2.5x. Here the length of this line segment LA is equal to 2.5x. Then I copied quadrilateral ALZB in a new page. This is the quadrilateral that I copied here. This is quadrilateral ALBZ that I copied from the original drawing. This quadrilateral ALBZ blocks this circle, so I copied this circle in the new drawing here. The quadrilateral and the circle has 4 points of tangency. That is to say, they touch each other at four different points. 1, 2, 3, 4. Okay, and then we have rule number 2. I presented to you rule number 2. And we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB, and according to rule number 2, they must be equal to each other. So PA equals to PB. So whenever you draw two tangents to a circle from a common external point, they must be equal to each other. In this case, PA equals to PB. We can implement rule number 2 in our drawing. We have the common external point, point A. From the common external point, point A, we have two tangents to the circle, tangent AN and tangent AM. And according to rule number 2, they are equal to each other. That is to say, AN equals to AM. So if AM is A, then AN must be also equal to A. Then we focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BT and tangent BN. And according to rule number 2, they must be equal to each other. That is to say, BN equals to BT. So if BN is B, then BT must be also equal to B. Then we focus on the common external point, point Z. From the common external point, point Z, we have two tangents to this circle, tangent ZZ, tangent ZT, and tangent ZG. And according to rule number 2, they must be equal to each other. That is to say, ZT equals to ZG. But so if ZT is C, then ZG must be also equal to C. And finally, focus on the common external point, point A, point L. From the common external point, point L, we have two tangents to this circle, tangent LM and tangent LG. And according to rule number 2, they must be equal to each other. That is to say, LM equals to LG. So if LM is D, then LG must be also equal to D. Then we added side AL to side BZ. From the drawing, it is very easy to see that AL equals to A plus D and BZ equals to B plus C. So in total, AL plus BZ equals to A plus D plus B plus C. We can change the order of the variables, and we get that A plus D plus B plus C equals to A plus B plus C plus D. We just change the order. Okay? And then we added side AB to side LZ. AB is A plus B and LZ is C plus D. So in total, AB plus LZ equals to A plus B plus C plus D. So those two expressions, they are both equal to A plus B plus C plus D, therefore they must be equal to each other. Very simple. So AL plus BZ must be equal to AB plus LZ. AL is 2.5x, so we substitute AL by 2.5x plus BZ. BZ is 2x, so we substitute BZ by 2x, and it is equal to AB. AB is 2, we substitute AB by 2, and finally plus LZ. LZ is 2 plus 1.5x, so we substitute LZ in the equation by 2 plus 1.5x, and finally we found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x. 2 plus 2 is 4 plus 1.5x. We subtracted 1.5x from this equation, 4.5x. Once 1.5x is 3x, so 3x equals to 4. We divided this equation by 3. And finally we found out that x equals to 4 over 3 units. That is to say, the radius of this circle x, it is equal to 4 over 3 units. And we know that the area of any circle, the squared brackets is the sign for the area, equals to pi times the radius square. If the radius is r, then it is pi r squared. In our specific circle, we define the radius as x, therefore the area must be equal to pi x squared. We just right now found that x equals to 4 over 3, so we substitute x by 4 over 3. So pi x squared is pi times 4 over 3 squared. Pi times 4 over 3 squared equals to pi times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, we found out that the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, the area of this circle equals to 5.585 units. Okay, repeat again, the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. Okay, thank you very much.